In this video, let us study how to solve these ordinary differential equations generated through any of the models such as Michaelis-Menten or Hill and so on, and typically you will see that you cannot solve these analytically, but you have to go in for numerical solutions based on different kinds of methods. So, how do we solve differential equations numerically? As usual, we will go back to Euler, right. So, in every module we will have to pay our respects to Euler. So, what did Euler do? He came up with a method for integrating equations. So, let us say dx by dt is f of x and x at t equals 0 is x naught. You can also write essentially dx by dt, you can write as xt plus delta t minus xt by delta t. So, on simplification this will give you x of t plus delta t is xt plus fx into delta t. So, let us just write this out. We have our rate equation which is basically dx by dt is some f of x, right, or we can say that dx by dt is x of t plus delta t minus x of t by delta t equals fx, which means x of t plus delta t equals x of t plus delta t into fx. If t equals 0, x of delta t is x naught plus delta t fx. X of 2 delta t will be x delta t plus delta t into f of right, and you can just extend this, which should actually be x naught, right. So, this is called Euler's forward method. There is also Euler's backward method. What do you think that is? You just have a small variation here. So, instead you say dx by dt is x of t minus x of t minus delta t by delta t. So, now the interesting part is x of t is x of t minus delta t plus f of x into delta t. You can actually even write it in the same fashion, right, in a very analogous equation, except that this now becomes an implicit equation, right. Why is it an implicit equation?
We don't know x of t and there is f of x of t.
Exactly, right. So, you have to now solve an equation in x of t. You have to iteratively solve it. Maybe you will use something like Newton-Raphson to solve this equation even. So, that is the backward Euler method, there is trapezoidal rule, there are Runge-Kutta methods and there are adaptive methods. There are many methods to solve ODEs, but essentially all of these methods use a particular logic. You have dx by dt is fx, right, and what do you want to find out?
X of t.
You want to find out x of t. In other words, what do you have and what is it that you want to reconstruct? You have the slope or the derivative at different points and you want to construct the original function, is that right? So, you know the value of dx by dt at x naught, dx by dt at some x1 and so on, right. Based on this you want to construct, correct, not at x naught, right, some t.
Depends on x also, right? dx by dt.
Yeah, or you can basically write it as, see, dx by dt is going to be f of x comma t essentially. So, at some x comma t. Here this is the slope, here this is the slope, here this is the slope, here this is the slope. Based on these slopes, you have to reconstruct the original curve. So, what do? You basically assume that the slope is constant over a small range, right, and then you use some value of slope for this entire range, right. So, trapezoidal will basically take half of these two, right. Runge-Kutta does something fancier, it will take twice of this and 4 times of this and divide by 6 or something like that. So, Runge-Kutta methods themselves come from different orders and so on. Why this is useful is that when you have a function that can behave a little crazy, you have to have an adaptive method, right, meaning what is your delta t? This is your t, right. What is the time step that you take, right. So, at this point you can afford taking a nice time step, at this point you can only take this much of a time step, right, and a good adaptive solver will choose your delta t. We will look at more of this during the lab session, because it will give you a better picture of why we need to go adaptive and things like that. So, we need so many methods because your function can be very complex and you have to adapt to it, right. You can't have one single delta t across the entire length of the function and so on, or you could have an aggressively small delta t to be safe, right, but that is again going to increase your computation. So, you need to use a good solver if you want to solve any of these differential equations. It becomes quite a trick, as we will see, right. So, this we will reserve for the afternoon session. We will try to do a small, we will have a lab wherein we look at how do we solve these kinds of ODEs using MATLAB.
So why do we need?
Yeah, you have a function dx by dt is some f of x comma t. What do you mean? No, you will be able to, you will compute the slope at different places, right, and then you use that to essentially trace out this entire function. If it were a line, one x comma t is enough to, but when you have like a more complex function, you need to have many more values of x and t. So, in this video you had a brief overview of how we go about solving ODEs and how you can use Euler's forward method or backward method to solve ODEs and so on. And in the next video we will go on with a lab wherein we write some simple iterative code to solve these ODEs and also use ODE solvers in MATLAB, something like ODE 15s.